morning everyone. The next speaker is someone you have hopefully already met over the tutorial sessions over the last 2 days. We have Vishwa Prakash, who is a PhD candidate at CMI. And well, yeah, please, Vishwa.
Thank you. Thank you all for showing up even on the third day, and special thanks to the organizers for inviting me here. Yeah, so I will be speaking more on matchings. So the first part will be on popular matchings, that you have seen popular matchings with two-sided preference already. So this is a fairly simpler topic where only one of the side has preferences over the other side. So we will see the setup in a while. So we will see the characterization of such matchings, and we'll see an algorithm for finding such popular matchings. And after the coffee break, we will be going into some of classical matching theory. So here it's simply graph theory. There is no preferences or anything. So I'm sure you might have seen some amount of graph theory in your algo course and done DFA, DFS, BFS, all these things. So we will be seeing, recapping some of the basics, and we will be seeing a very nice theorem called as the Dalmas-Mendelssohn decomposition. So that's the plan. If you have any doubt at any point of the time, please feel free to just stop me there and just ask your doubt. Okay. So starting with the part 1. So you all might have encountered this problem in your life at some point. So there are some n agents, we'll call them the applicants, and there are some hostels available in your campus. Some hostel rooms are better. There is one new building which has better rooms, and there are some old buildings that doesn't have an AC and so on. So the rooms do not have a preference over the applicants, but the applicants have preference over the rooms. So for example, for her it is the first preference and second preference and so on. So the list need not be complete. So there are some rooms such that I will never go to that room. I would rather stay at home and work from home. So these are the preferences. We want to find a matching that is in somehow fair, like it such that it doesn't create a protest among students. So this has many applications. It could be applicants and tasks. I mean, for an organization, the task needs to be completed. We don't care who does it. But it can be the people who are doing the task will have preference over them. So this is the problem that we will be considering today. Yeah, suppose an allocator gives this allocation. So applicant 1 is matched to this room and this red matching. Okay. So what is wrong with this matching? Thing is, once allocated, the applicants will see that, there is another matching, the green matching, where it makes more people happier. So that is, let's see the voting here. So there is N, the red matching, and the N, which is the green matching. So for the first person, N is better. It gives the first choice, and the M gives second. So she will vote for N. Okay. So for second one, it doesn't really matter. He is getting both, the second room in both of the matchings. So he will not vote. So but for the third, fourth and fifth, you see, they are getting better rooms in their green matching compared to the red matching. So what will these three people do? They will organize a protest. They will go to the allocator and say that, see, here is a allocation which will make us happier. We don't care about the people who are losing some of the rooms. These people, these three will go and organize a protest. So when is an allocation, allotment a good allotment? We say it's good if the allocator can say the following. That is, so these protesters are saying, see, there is an allotment that is better for all of us. So the allocator must be able to say, see, the allotment you propose will trigger another protest with at least as many participants as your group. I cannot entertain this new allocation that you are proposing Because if I do that, like another set of people who will come and protest, and that group is also as big as you. So what we are here looking at is again popular matchings. So if we have a popular matching, the protest size will be small. I mean, they cannot come up with another matching which makes more people happier. Is that clear? So we are considering popular matchings with one-sided preference. So a matching M is said to be popular if there is no other matching N that is more popular, that gets more votes than M. There could be multiple popular matchings, but a matching is called popular if there is no other matching that beats this in number of votes. So for the last 2 days, I mean in the yesterday's lecture, you all saw popular matchings with two-sided preferences, right? Do you recall some of the results that were discussed yesterday and in the tutorial? So does popular matching always exist in two-sided preference? It does, right? Then easy proof is that stable matching is a popular matching, and stable matching always exists because you can run Gale-Shapley and you have seen the proof that it gives a stable matching. You also saw that it's a popular matching. So it always exists, right? So popular matching will always exist and can be computed efficiently. This is when both the sides have preferences. So here I am saying the other side doesn't even have preference. So in the allotment case, that is one-sided preference, does a popular matching always exist? First thing, like it's not obvious from yesterday's result whether it should exist in this setup or not. Is the question clear? Yeah. So I want you to all, like, for a second think about this, and what do you think might be the case? Like, it exists for two-sided preferences. Do you think would it exist for a one-sided preference? And it seems like a simpler setup. It should exist, right?
Can we look at two-sided preference
Yes.
as one-sided, like not all empty preference?
Yes, that is one way to go about it. You take two-sided preference, you were allowed to have incomplete list, so just delete the list from the other side and find a popular matching. But you see, the popular matching, the popularity, the other side had a chance to vote in this one. Here we are only taking one-sided vote of the applicants. Do you think that would make any difference?
We can assume that the other side simply either all voted yes or all voted no, so like it does not make a difference between the two.
Yes, that you could define it that way, but here is a simple example that I want to show. There are 3 applicants, A1, A2, A3, and there are 3 rooms. Everyone prefers it identically. Everyone thinks room 1 is better, room 2 is the second best, and room 3 is the worst. Okay? Take any matching, take any allocation. This is the allocation I want to take. Is this a popular matching? Can you come up with a matching which is more popular than this? Yes. Just I promote this one. So, but this is not a matching. So I promote this one. That's not. So I demote one. I make 2 people happier. One guy completely like.
One guy has
Oh.
to give it up.
Yeah, one guy. Oh, sorry. I think. Sorry. Okay, this should be R3, R2, R1. And, assume that this is most preferred, this is less preferred, and this is the. Okay, I just messed up the slides, but that's okay. Assume that R3 is the most preferred, R2 is the second preferred, R1 is the worst.
The next slide can be the first slide and this slide can be the second slide.
Yeah, some here. Yeah, so the promoted 2, demoted 1. This is more popular than the previous one because 2 people will vote for this matching over the previous one. But is this popular? Again, it is not. We can do the same trick. I'll promote this, and I will demote the second one. So whatever allocation you give, even this is not popular because I can promote 2 and I can demote 1. So whatever matching you give me, there is another matching where I can make two of the agents happier, one of the agent sad. So there is no popular matching here. Like popular matching need not necessarily exist in this setup. Is the example clear to you?
Two people are always being happy there, and one is not happy.
Yes.
That is the sense. So then why is the popular matching not existing?
So suppose there is a popular matching. You give me this is a popular matching. So why is it popular? There is no other matching which gets more vote, right? So I am computing another matching where it gets more vote. Where I take this matching, the supposed popular matching that you gave me, I will promote two people. I can always promote two people
Okay.
in this, and the one person I can demote completely. That will get more votes.
This is the titration. If you are going right, then we are demoting.
So this slide just for the, in this slide assume that this is the first
Yeah,
choice,
okay.
this is the second choice, this is the third choice.
Right.
Assume that R3 is preferred over R2 over R1.
Okay.
I should have just simply flipped it, but I
Yeah,
think.
that's all.
Is this clear? That popular matching need not exist. So what are we doing now? Like, I mean, we are not, it's not guaranteed to exist. So what we want to do is, if it exists, we want to find one. Is the goal clear? So goal is to find a fast algorithm, fast meaning polynomial, to check, given an instance, is there an algorithm that can quickly check if the instance admits a popular matching or not. You already saw one instance where it doesn't admit, but there might be instances which does admit. Okay, you want to quickly figure out, is it there or not. Another goal is to see what kind of instances admit popular matchings. So we want to see a characterization of it. You cannot go on with all, take any two matchings and see if this is popular or not, and there are exponentially many matchings. You can't do this. So we want to characterize these popular matching, characterize the instances which admit popular matching. And finally, yeah, so if it does exist, we want to find them. So this was answered in this paper. The title of the paper is simply popular matching. It appeared in Soda 25. For people who don't know, it's a very top conference in theoretical computer science. So these four people gave the answer: Abraham, Irving, Kavita and Melhorn. So we will be seeing some parts of this result today. So do you have any questions? Like, so you are convinced that popular matching doesn't exist. Okay. Let's see, look at the algorithm. So firstly the model. So incomplete lists are allowed. People can have incomplete lists. And strict ordering. We are in the case where there are no ties. So like given two rooms, either room 1 is better than room 2 or room 2 is better than room 1. It cannot be equal. And just for the sake of like simplicity, what we are going to do is simply introduce dummy last choice for everybody. So that is, they are dummy rooms, they don't exist, and they are different for each of them. If they don't get an allotment, we are going to simply allot it to the dummy room. In this way, we can simply deal with complete matchings. We can say everybody, in this instance, everybody is going to get a room, but if they get matched to the dummy room, we are going to say in the original allocation they did not get a room. They have to work from home. Okay. So getting matched to the L room here is same as not getting any room. But for the algorithm, it will be cleaner this way. With me? Okay. So first we will see a characterization of instances that admit popular matching. So for any applicant A, let f of A denote the first rank room, the most, the favorite room on A's preference list, and that is A comma f of A is the rank 1 edge, and we are going to call any room R as F room. Now let F inverse of R denote the set of applicants for whom that is the first rank choice. Okay. Now first we are going to prove one small lemma. It's not immediate, from the, when you look at it. If M is a popular matching, then every F room is matched. It cannot, if a room is first choice of somebody, it must be matched. Not only that, it is matched to somebody that treats it as their first choice. Okay. So if you give me a matching and claim it is popular, I can just first sanity check is to make sure is every F room matched to somebody who treats it as an F. You can check a room is F room or not, just simply going through everybody's preference list and seeing is it the first choice of anybody. If it is first choice of anybody, it's an F room. And then if you give me a matching, I can simply say is it matched to somebody who treats it as a first. So we will first prove this theorem, lemma. So first of all, an F room must be matched. If it is not matched, we will simply pick one agent who treats it as a F room, and he must be matched to some not his first choice. We will simply promote him to this F room, and that is more popular. So it must be matched. That is like obvious. Is it okay? So then, suppose it is matched to someone who treats it not as the first choice. So consider R. We are looking at room R. So you see room R is first choice for A1 and first choice for A2. So it is definitely an F room. But it is matched to some AI who does not treat it as a first choice. Like, I mean, AI has R star to be the first choice. So can you see that this is not popular? I mean, take some 10 seconds. Okay. Okay. There is A1 and AI.
If you just switch the rules of A1 and AI, then and keep everything as it is.
A1 and AI, you want to switch the rules, meaning AI gets R prime.
Yeah.
It might be somewhere later.
Yeah.
Okay. So he is going to vote against this allocation. He is going to vote for this allocation.
So like votes will either cancel
Yeah.
or it will be more popular.
Yes, we want to show that this is not popular. We want to say strictly it increases. We don't want that either same path. I mean, we just saw the trick in that example. So we simply promote this to R. Like this is R prime. There is a agent. I mean, we simply pick an agent, an applicant for whom it is a first choice. It's matched to something else. We will give it R, but it is clashing now. We will promote this also to R star. Two people are promoted. Whoever has R star, now we are demoting all the way to last choice. I mean, this is definitely not matched because it is unique to AJ. It's a dummy. So basically we are unmatched. So here both A1 and AI is going to vote for this new matching, and AJ is the only person who is going to vote against it. Is it okay? So we know that this is necessary for a matching to be popular. So what else is necessary? So here 2 promotion, 1 demotion, which means it's not a popular match.
Excuse me, can I take a moment in the previous slide?
Yes. So these slides will be shared to you. So I mean, don't worry about taking notes. You can just have the slides.
But what if somebody else had
Yes, somebody might have R star. For them, we are going to demote all the way.
So here again AJ is unhappy.
AJ is unhappy, but 2 people are happy. I mean, the assumption was that it was matched to somebody who doesn't treat it as a first choice.
Given
So whatever is their first choice, we are going to give it to them. And R will be free. Whoever treats it as a first choice, we are going to give it to them. So both A1 and AI is going to be happy. And AJ is going to be sad, but we are 2 versus 1.
So that is not system not a popular match.
I know. I don't know if this is a popular matching or not. All I said is here is a matching which is more popular than the previous one. So therefore the previous one is definitely not popular.
Right.
Yes.
Sorry, so are we assuming that every room is popular for somebody?
The popularity is defined for a matching. Like we don't know what's
Sorry, I think the first choice for somebody.
Sorry, could you repeat that?
Are we assuming that every room is the first choice for somebody?
No, we are not assuming. There could be a room which is last choice for everybody, or not the first choice, like some fifth choice for everybody. That's we are not assuming anything.
So when we move AI from R to R star,
Yes.
R might just be free, and then we don't need to bother with anything else, right?
Yes, that is also true. Like if R is free, I mean, that was the previous case. Like I mean that is also okay. So is it clear until here? So we saw that this is a necessary condition. Why is R? No, if it is not matched, find an agent who treats it as a first choice. Then simply give it to them. Whatever they are currently matched to, instead of that, give their first choice.
Yeah, that will obviously be a promotion.
Yeah, everyone is going to be like same. For this person, he is going to vote, yeah, this is better for. Right? So the next one is like, for every applicant A, let S of A be the first non-F room in A's preference list. So you take A's preference list, the first room is going to be my own first choice. I go to the second room, I see is it anybody's first choice. If it is, that is an F room, not mine, but somebody's F room. I go to the next room in my preference list and see is that an F room for anybody. So the first room that is not F room of anybody is called as the S room. Is that definition clear? Yeah. So, I mean, obviously F rooms are disjoint from S rooms by definition. You call it a room S room if it is nobody's F room. In fact, the first room in every candidate's preference, which is nobody's F room, is the S room. Is that okay? Yeah. So, like for example, this A1 has this as the preference. So, this is of course A1's own F room. But maybe there are few rooms which are F rooms of somebody else. The first time you get a room which is nobody's F room, you define it as the A1's S room. S of A1. This is the definition of an S room. So, the minute you have this definition, there is another necessary condition that crops in, which is let M be a popular matching. You consider any popular matching. Then for every applicant A, the matched room, M of A is the room that an A gets in matching M, can never be strictly between F of A and S of A. I mean, the room he gets, if you are claiming a matching is popular, then for any agent, check the room that that agent is getting. It cannot be strictly between his F of A and S of A. Why is this? We'll see the proof. Like, suppose this is R5 is F room and R7 is S room. Okay? So now it is strictly between. Suppose for the sake of contradiction, we are assuming that R3 was allocated, it is strictly between R5 and R7. So these are all F rooms. By definition, this is an S room, which means everything before that is an F room. We saw the previous lemma, an F room must be matched to someone who treats it as their first choice, not to this person. So this is simply contradicts the previous lemma. So we have this another necessary condition, that is for, I mean, you look at any matching, if you are claiming it is popular, I am going to look, I mean, for every matched room, it cannot be strictly between F of A and S of A. Is that okay?
Can you repeat this
Argument? Like, see, for the sake of contradiction, assume this is a popular matching. I mean, I am just looking at one agent where this condition is not satisfied. So this is A's first choice, this is S room. So this is, suppose this is the room that is allocated, that is strictly between both F room and S room. Okay. So if this is the S room, by the definition of S room, everything before is an F room. Do you agree? That is how we defined S room.
Yeah. Oh, I understand.
And what is an S room? The first room that is not F, which means everything behind that S room is an F room. It is first choice of somebody.
R3 is an F room. It
For-
must be matched to someone who has R3 as the first preferred.
Exactly. That is what we saw in the first lemma.
Okay. Okay.
But here it is matched to somebody who does not treat it as a.
Right.
It is strictly between his own F room and this thing.
Yeah, yeah.
This cannot be possible because it contradicts lemma 1. Yes?
But can you be sure that the F rooms are like in a particular sequence? Like there can be some F rooms later on also. Right?
Yes, no. The thing is we are defining S room as the first room, like you are going in a sequential manner. To define S room, the first room that is nobody's F room is the S room. So this sequence you are guaranteed by definition. It cannot happen that first there are few F rooms and there is a hole here that is nobody's S room and then there are more F rooms and then there is S room. Then this hole will be the S room. The definition of S room is you start from the first room, you keep going on, like the first time when it is not anybody's F room is the S room. So you are guaranteed that everything before is an F room.
Will there be some F rooms after S and J?
Yeah, there can be. We don't care about it.
So can there be an allotment between SA and F room after that?
Yes, we will see that in the next. That is a very good question. There could be some F rooms afterward, and maybe this lemma simply says that it cannot be strictly. Can it happen that it is matched to someone who is someone is getting some matching where they are matched to some room after S room? That is your question.
But that cannot be an F room.
If B can be mapped to an S room, that can happen.
That can happen. Yeah. So this lemma simply says yes.
How can there be F rooms after the S room?
Yeah, we will see that in the next lemma. It will immediately answer all these questions. The second lemma is nobody. If you are claiming a matching is popular, then nobody is going to get anything worse than S room. Is that okay? So we will see the proof of this. Suppose that this is the preference of, and suppose for the sake of contradiction, see for A1 this is the first choice and this is all F rooms and this is the S room, and A1 is getting matched to a room which is worse than S of A. Okay. So which means like if S of A is free, S of A is not matched to anybody, you can simply promote it, and that therefore this matching is not popular. Suppose it is not free, which means it is matched to somebody here. I mean B's S room could be anywhere. I am not claiming B's S room is this. I am saying whatever this room is, A1's S of A, it is matched to somebody, which is why we are not able to immediately promote it. Okay. So for B, can this be this S of A lie here?
But AJ can be less for R2.
Yeah, no, I'm asking a simpler question that can this happen? This S of A is the first choice for B. No, because we just saw that F rooms and S rooms are disjoint. If a room is S room for one person, it is nobody's F room. So therefore it is not this guy's F room. So it must be, there must be some rooms before this.
Right.
Right. So S cannot be first choice of B. And we will see where is the first choice of B. Maybe it is matched or maybe it is not. If it is not matched, we can simply promote this. S of A will be free, we can promote this. Both will be happy, there is no problem. But if it is matched, suppose it is matched to AJ.
So we'll demote AJ. to
Yes,
the-
exactly. We will promote A1, we will promote B, we will demote this person. Like he will get better one, slightly better S of A. He will get excellent room. This guy is going to get worse room. 2 versus 1, again this is not popular. So nobody can get anything strictly between S and F. Nobody can get anything after S. So what should they get? Either their first choice, either their first choice or their not second but S of A. Right. This is necessary. If you are claiming this is a popular matching, this is a check I am going to do to make sure that it's not obviously not popular. Huh?
Your S of A is with respect to A1.
Yes, S of A is with respect to A. Like for every agent we are defining S. Is that okay? Yeah, so we have lemma 2, lemma 3, we are just clubbing both the lemmas. We have M is popular, then for every applicant, the matched room is either F of A or S of A. Okay? So this is necessary, but it's not clear, is it sufficient or not. So you know what's a necessary and sufficient conditions, right? Like a simple example is like every cycle, I mean a graph is a cycle, suppose, simple cycle. And it is necessary that it has, no, suppose consider a path. I am claiming a simple path. It's necessary that it has n minus 1 edges. But is it sufficient to have n minus 1 edges? Is there something else which is not a path which is also n minus 1 edges? Tree. So having n minus 1 edge is necessary but not sufficient. I just wanted to make sure everyone knows necessary and sufficient. So this is necessary. Is it sufficient? That is. So that's the final characterization we will have. That is, a matching is popular if and only if every F room is matched, and for any applicant it is matched to either F of A or S of A. Okay. So the only if part you have already seen. It's necessary. I mean, if one of these is failed, you saw the proof that it's not popular anymore. But if this is matched, if these both are satisfied, it's not sure. Is it guaranteed to be popular? Is there some other matching which is not popular that also satisfies both of these? Okay, that is what the if part we will be seeing. It happens that this is enough. Like if you take a matching and make sure both these conditions hold, you are guaranteed that it is a popular match. That would be a characterization of instances that admit popular match. So it's slightly tricky, so pay attention. So let M be a matching that satisfies both conditions 1 and 2. And suppose there exists another matching N that is more popular than M. Okay? I mean, here is a matching M that satisfies, but it is not a popular matching. Because there is N which is more popular. So let A be an applicant who prefers, oh sorry, this should be M prime. Okay. Who prefers M prime over M. I mean, it is more popular means there is at least one agent who is voting for it versus this allocation. Let's look at just one applicant. Maybe that applicant is getting R prime in M prime, but R in M. This A is voting for M prime, so R prime is better than R for agent A. So we will see that. So for agent A, so I am denoting M with this yellow and M prime with white. So A is getting R in M and R prime in M prime. Okay, and we know that M satisfies both these conditions. So this is either F room or S room. Can it be F room? No, it's not the first choice. So it definitely must be S room. But the minute you see this is an S room, you also know that all the before ones are F rooms. That's a mistake. They are F rooms. Okay. So which means these are all F rooms, and we know that M satisfies this first condition also, that F room must be matched. So in M, in yellow, this R prime must be matched to someone who treats it as an F room. So suppose it is matched to somebody here. Okay. So then in A prime, in M prime, A prime cannot get R prime, because in M prime, A is getting R prime. So he must be getting something worse. Yes?
Shouldn't R prime be F of A?
R prime be F of A, why?
Because it's necessary that either it's matched to F of A or S of A. And we know it's not S of A, so it should be F of A.
No. I'm talking about M. In M prime, okay.
R prime is a
Yeah.
Even if R prime is for M prime.
Yes. You are right. This R prime should be here.
Yeah.
But that is okay. There could be another person who also treats this as an A prime.
No, when we are moving the backward direction, then we should not assume that M prime satisfies 1 and 2.
Yeah.
But M prime is simply more popular. It's not the popular match.
Yeah.
Okay.
So we cannot apply necessary condition for M prime.
Okay.
Yeah, we are only claiming that M prime is more popular than M, not necessarily the popular matching. If it is the popular matching, we could have applied the necessary condition, but that is okay. I mean, we don't need any of this in this proof. We simply say that M satisfies these two conditions, therefore R prime must be matched to a somebody here. So S of A is going to, I mean, A prime is going to vote against M prime. So you see this R prime is unique to A. Like if there is another agent who is also voting for M, it is not because they are getting R prime, they are getting something else because R prime is given to A. So for A, there is A prime. Like if A votes for A prime, there is a corresponding another agent, applicant who votes for M instead of M prime. For everybody who claims M prime is better, there is a distinct corresponding applicant who says no, for me M is better. So where is the more votes coming from? It cannot happen. No. We are only assuming that, we are not saying that M prime is a popular match. We are saying M prime is more popular than M. That's all. If you claim that M prime is the popular matching, then you could apply the necessary condition that you check. So we cannot say that R prime cannot be between these two.
But actually, you are assuming that when you're saying that between the F room should be matched.
That is, I am guaranteed that M satisfies both 1 and 2. Therefore, this cannot, so M satisfies both 1 and 2. It cannot be S room or K. I am assuming M satisfies. I am not because it's popular or anything. That's the assumption of mine. Is this okay with everyone? Like, so you see this is a characterization. The minute we have this characterization, we are almost done. We have an algorithm. So how do we do that? Like, so this is a characterization. So take a preference list. Okay. So construct the corresponding graph. I mean, this is the input graph. Okay. I'm just attaching these dummy L rooms, and I'm connecting everybody to the L rooms. So this is the input graph you have. So first find all the F rooms and S rooms. That's a very simple task. You don't have to compute it. Like, see, R2 is its own F room. I mean, R1 is A2's F room. R1 is again A3's F room. R3 is A1's F room. You mark all F rooms. Then you go here. The first room, that is like R1 is already F, R3 is already F. So this is nobody's F. This must be L. S room. S room could be L room. We don't have a problem with that. But here it is not. You see, R3 and R2 are first choice of people, and the first thing that is nobody's first choice is R. We mark all F rooms and S rooms. Okay. We simply mark these edges. Like for F rooms, I am denoting by green. Okay. And S rooms I am denoting by red. I am just deleting everything else. We can I am calling it the reduced graph. We can simply deal with this graph. I mean, we are guaranteed that if you have a popular matching,
it will consist of only these edges.
These edges, right? Not just that, everyone here will be matched because I am also keeping the. I mean, if I say everyone is matched, that is enough here. Every applicant is matched. If they are matched, they will be either matched to F room or S room.
Right.
So I am looking for a perfect match. I mean, applicant perfect matching here. Is that okay? So that is, from this characterization, it is immediate that it is popular if and only if every F room is matched here. All the vertices that have a green edge incident on it must be matched, and it's an applicant perfect matching in this G prime. G prime is the new graph where I have deleted all this useless edges. If you can find me that, we are done.
What
applicant perfect is simply that a matching which matches all the applicants. And a perfect matching is a matching that matches all the vertices. So here A perfect is a matching that matches all the vertices on the A side. A B perfect is matching which matches all the vertices on the B side. So we are looking for an applicant perfect matching. So because if it is applicant perfect, everybody is matched, and because there are only two edges, it must be matched to either F room and S room. And this condition is that every room that has a green edge on it must be matched. We can check this in polynomial type. How? So construct the reduced graph G prime, and if G admits an applicant perfect matching, just find one applicant perfect matching. Here is an applicant perfect matching. Okay, where every applicant is matched. Okay, it's not a popular matching yet because there are rooms which are first choice of people which is not matched. So for every F room which is not matched, take somebody who treats it as an F room and promote them. Okay, it is still applicant perfect. Look at the next room that has a green edge on it. Find one person who treats it as an F room. This is the only person. Promote him, and then look at another room that has a green edge. Fine, promote them. So once you are done with it, you will still have an applicant perfect matching, and every F room will be saturated. Like if every F room is saturated, it will be saturated. Then you simply return the matching type. If you cannot find a applicant complete matching, you say the original instance does not admit a popular matching. That's all. This is the algorithm. So what happens when there are ties? I'm not going to cover this in this session, but we saw that for stable matchings and popular matchings, when there are ties, we could handle them somehow. Right? We were making arbitrarily breaking ties, and we were just running the gauge and so on. So most of the machinery that was developed for without the ties would simply work with some playing around with that. But the thing is, this algorithm and the characterization does not work for the case when agents can have two rooms which are the same. Is it okay? I'm not going to go to the proof of it. So the authors in this paper, they also handle the case when there are ties, that is more involved, and they use a very nice graph theoretic concept called as the Delmarche-Mendelssohn decomposition, which will be the topic of our second lecture. Okay. To give a different algorithm, and it's not as fast as this, but it is still polynomial.
And it works for ties.
Yes, that is for ties this works. It's a slightly slower but still polynomial algorithm. So this is the paper. You can. I believe it's a very easy paper. Don't be scared to read a paper. Just you should be able to follow this, especially after this talk. So it will be. It's a very good paper. It's Soda print 2005. So you can have a look at that. Thank you. So if you have any questions, feel free to catch me while having coffee. And hope you all also show up for the next session, where we will be talking about this Delmarche-Mendelssohn decomposition. It's a very nice theorem that when you look at it for the first time, you won't believe it. This cannot be true. But once you see the proof, it will be very enlightening. And you can use it not for just popular matching, some wide variety of applications. It's a 1952 theorem. Yes?
So in the algorithm, if you can go to the previous slide,
Yes.
like why do we have if G dash admits? Like since we've introduced else,
Yes.
L1, L2,
Yes.
can't we say G dash will always have an applicant perfect match?
See, where is L2 here? In this particular one. So we only have S's. Like if an L room is, if an is nobody's first second choice, it will not appear here. Right. I mean L2 is not here. I mean I will go back to this one. See, we missed L2. It can happen that A2 is never matched. If it is not matched, it will not be matched here because there is no L2 to go here. So it must be an applicant perfect match. I mean, if you don't have one, then there is no popular matching.
And in the applicant perfect matching that we have, we only move like we only check for F rooms which are not matched.
Correct. Yes. If an F room is not matched, we promote it. Like, and then if it is an F room because somebody treats it as an F, find arbitrarily pick one person who treats it as an F, give it to that person. Yes.
Are we taking only the L rooms which are S rooms?
Yes.
We are taking all the S
No,
rooms.
we are taking only F rooms and S rooms. If some of the S rooms happen to be L rooms, we are taking that. We are not taking all the L rooms. We are only taking S rooms. Some of it here happen to be L rooms, so it just naturally shows up. Yes.
Both A2 and A3 both were matched to their S rooms. So
Correct.
when you promoted to R1, why did you promote only this?
I arbitrarily picked. There is no choice. Like I could have promoted this person, in which case A2 will still have an S room, and that is also popular. Like this is another popular matching. Because it satisfies our characterization. We know that is sufficient. Yeah. Okay, see you all again after the break. Hello everyone, welcome back. So we will be continuing the sessions on our study of matching theory. So but now we are done with matching with preferences. Like there are no like agents having preferences over the edges. So we will be considering a much simpler, much classical and more applied I mean, it's applied in more cases. Yeah. So, are there
Yeah,
I can at least the first things are definitions. So we'll have some definitions like what's a graph? It's simply vertices and edges. Edges is a subset of V cross V. Here are some example graphs. And what's a matching? It's simply set of edges that are not adjacent. Okay. So, yeah, this is the formal definition of matching. So here, note that there is no preference for the edges. It's a much simpler. Like we saw with two-sided preference, one-sided preference. Now there is no preference. Yeah. Here, is it like I have highlighted some of the edges. Is it a matching? No, because it is two edges are adjacent. So, but here is a matching set of edges that is a matching. Simply just two edges that are not touching each other. So, you keep that. So, a matching is called maximal if it cannot be extended by adding any more edges. That is like if you try to add any extra edge, it will break the matching. So is this a maximal matching?
No,
V1 to V6 you can add, or you can add V6 to V7 and it will still remain to be a matching. So therefore this is not a maximal matching. So here I added an edge which is now is this a maximal matching? Yes. You cannot add any more edges. So how many edges are there? There are 3 edges in this matching. Okay, just it's a maximal matching. You cannot add any more edges. Just 3 edges. A matching is called maximum if it has the largest possible number of edges among all matchings. Is this a maximum matching? It's not a maximum matching because here is another matching. I replace this edge with these two instead. Now every vertex is matched, but not necessarily always. This is a maximum match. You see that maximal need not be maximum. Right? I mean, maximal is a very naive, greedy technique where you just keep applying. I mean, picking edges and see can I add this or not. And whatever matching you find, it is going to be maximal, not necessarily maximum. It's not obvious how to find maximum matchings yet. The matching is called perfect if it matches all the vertices. Here it's a perfect matching. Right? It's matching all the vertices. So I am not considering, though this graph is a bipartite graph, these definitions are for any graphs, not necessarily bipartite or anything. I haven't even defined what is bipartite. It's just graphs. So not all graphs admit perfect matching. Here is a very simple graph. There cannot be perfect matching. You cannot find a matching that saturates all the vertices. This is the best you can hope for. Just pick one edge. You cannot add either of them. It's a perfect match. So we will play with matchings and get comfortable with it. So here is a graph. It's made of vertices and edges. And here is some matching. I call it the M1. Okay. I don't know if it is maximal or maximum or anything. It's simply a matching. And here is another matching, a different matching. So not all the edges are different. This edge was not different. Some edges are different. Okay. So now I will just combine them. I will just union both of them. I mean, in union I am going to keep every vertex, but I am going to, like if an edge is present in either of red or green, I am going to keep it. So this is how the union is going to look like. There are a bunch of red edges, some green. This is there in both. Okay. This is just union of two different matchings. So now I don't want these both edges. So I'm going to take symmetric difference. So if you have forgotten what is symmetric difference, here is a representative image. Just take the union, delete the intersection. Okay. So the vertices will remain, but the edges I'm just keeping. So I wanted to just stare at this diagram now. What did I do? I took two matchings. I didn't have any choice. I just arbitrarily picked two choices and took this symmetric difference. Okay. And this is the structure I got. And there is something nice about this structure. Yes, it's a path and it's a cycle, but we'll see why. Like, so we'll take that graph over there. The symmetric difference of any two matchings is a graph in which every component is either a path or an even cycle.
So, any vertex with degree 2 will be preserved.
Correct. Yeah, that is. So here, every vertex, how many edges can be there in this symmetric difference? It can have at most 2.
Yeah.
Either from M1 or from M2, or it did not get any. I mean, either it got from both.
Or it's got nothing.
Yeah. So at most 2. There are vertices of degree 0, degree 1 and degree 2. So if there are degree 1, degree 2, degree 0, that's the best, the maximum degree. Then I claim that it must be either paths or cycles. So why is that true? It's a simple proof. Like every vertex in this symmetric difference is of degree at most 2. And the components must be either a paths or cycle. Not, I haven't shown this even. This, I mean, verify this at home. So it must be paths or cycle. And every cycle gets same number of M1 and every cycle, every vertex here has both edges, one from green, one from red. So it has to be even. I mean, if you take any cycle, every vertex here is getting two edges, one from M1, one from M2. So cycles needs to be even, path need not be. But overall, M delta N will be paths or cycles which are even.
Every vertex gets two edges, but that doesn't mean the cycle has to be even.
Yes, and it is a cycle and it's a path, but why is the cycle even? Because it is getting one from green, one from red, which means a number of red edges and number of green edges are same in a cycle.
So the edges are even. So it
Yes.
has to be even.
Yes. And for every vertex there is one red, one green. So overall there are the red edges and green edges must be the same number.
Rather, if you think about it as the edges in the cycle, two edges and edges cannot be the same.
Correct.
Yeah.
It is alternating, like it's red, green, red, green. It's always an even cycle. Like if it would have two colors hitting each other, then it's not a matching. That would happen only in odd cycles. So this is, I believe most of you have seen this like in second year or first year undergrad courses. So I just wanted to recap this. So now this also you might have seen, but anyway I will brush it up again. So given the matching M, an M alternating path is a path in the graph that alternates between edges in M and edges not in M. Any path, I'm not talking about the longest path or anything, simply a path that alternates between a matched edge and an unmatched edge. Here is a simple here is a simple alternating path. It starts here, it matched edge, unmatched, matched. It's an alternating path. Okay. So I call in a matching an M augmenting path is an M alternating path, but it is special. It starts with an unmatched vertex, ends with an unmatched vertex. I mean, given a matching, you can define what is an M augmenting path. Right? So is there a augmenting path here? Let's consider this graph. So here look at this alternating path. This also alternates between unmatched edge, matched edge, unmatched edge. It can go on for longer. I'm just considering a small example. But it is not just alternating, it's also augmenting. Why? Both the endpoints of this path are unmatched in the matching. So is the definition of M alternating and M augmenting clear? M augmenting is a special alternating path where both the endpoints are not matched. So why do we care about M augmenting path? So Claude Burge showed that any matching M is maximum if and only if there are no M augmenting paths. It's again a characterization, right? So have you guys come across the proof of this? Like famously known as Burge's lemma, like. So we'll quickly see that one. So suppose M is maximum. If there is an M augmenting path, what can you do? Take an M augmenting path. It starts with an unmatched vertex, ends with an unmatched vertex. You take this edge and you simply switch, like instead of taking this edge, you take this edge. Instead of taking this, you take this, and so on. If it is an M augmenting path, it will have more non-matching edges than matching edges. The first edge will be a non-matching edge, the last edge will be a non-matching edge. Right? You can increase the matching. Is this okay? Yeah. So we can simply take, so the necessary part is clear. Why is it sufficient? Suppose it is not a maximum matching. I mean, I am claiming that this is enough. This is sufficient for it to be maximum matching. Suppose it is there is some M which does not have any M augmenting path, but is not maximum. So let M prime be some other maximum. You simply consider the symmetric difference of M and M prime. So here M prime is bigger than M, right? Because I am assuming M prime is a maximum, M is not, which means by definition M prime is bigger. When you see the symmetric difference, you are considering all the matching edges, and if a matching edge appears in both, you are deleting. So this extra edge has to appear somewhere, right? It cannot appear in the cycles because cycles have same M edges and M prime edges. So it must appear in the paths. If path has same M edges and M prime edges, it cannot be augmenting. It starts with the red edge and it ends with a green edge. A green edge is an edge which is not in red edge, so it cannot be augmented. So one of the path must be an augmenting path. So is the characterization clear? I mean, this is enough. I can just check for M augmenting paths. If there are no M augmenting paths, I am guaranteed that it is a maximum matching. Yes?
Can you explain again why symmetric difference of M will must have an augmenting?
Yes, you take. So you are claiming M prime is a bigger matching. I am saying M is not maximum, so M prime is a maximum. So it should definitely have bigger. It's a more number of edges. You take the symmetric difference. You saw symmetric difference will have all the matching edges, but if a matching edge is present in both, they will not appear. So if M prime is bigger, then there should, in this symmetric difference, assume M prime is red, M is green. There should be more red edges than green edges. But cycle cannot have more edges, red edges and green edges, because we know they are even. So one of these paths must have, at least one path should have more red edge than green edge. How should it look like? It should start with a red edge, end with a red edge. Okay, that is an augmenting path. These red edges are not present in the green matching. So for green, it starts with a non-matched edge and match, non-matched, matched and non-matched. Finally, it ends with a non-matched. This itself is the definition of augmenting path.
If this edge appears only like it's just one red edge, nothing like no green edge attached to it.
That you can then add it. That itself is enough. Like that edge is not present in M at all, and these edges are not matched. You can simply add this edge. So M is not maximum. A one length alternating path, augmenting path is also okay. Like so until here everything is clear to you, because The next we will be seeing something more interesting, and hopefully you have not seen that before. I want everyone to be comfortable with this much definitions. So just to see why do we care about augmenting paths, like you start with some matching, possibly empty matching. Check if there is any M augmenting path. If there is no M augmenting path, we know it is a maximum matching. We just saw the characteristic. If there is, find one. I have put it in a black box. I am not going into how to find one. You can do BFS, DFS many ways. Find an M augmenting path. Then augment. Augment meaning switch. Like take that path, instead of the matching edges, take the non-matching edges. It will increase the matching at least by 1. Keep repeating that until you run out of augmenting paths. When you do run out of augmenting paths, the matching does not have any augmenting path. You have seen the character, it must be matched. It will give you your first algorithm to find maximum matching. Is that so? This is why we care about augmenting. So basics are done. If you have any questions, let me know right now. Yes.
Can you explain, prove that the previous algorithm will terminate in that loop?
It will terminate because every time you are adding 1 edges, and you are checking is there an M augmenting path or not, and maximum matching exists by definition. Like the matching exists, so find the one which is maximum. If it exists, then it is not going to have any augmenting path. So there is a point where this will stop. But it's good to do such sanity checks, like when you encounter an algorithm. Like the first thing is, does it terminate? Forget about the running time. Yes. So now, our interest is only on bipartite graphs. No? So bipartite graph is a special graph where you can partition the vertices as A and B. If and only, where there are no edges in vertices of the same part. There is part A, part B. This is the definition of bipartite graph. I hope everyone has seen bipartite graphs before. Yeah, there is a very simple characterization of this bipartite graph as well. A graph is bipartite if and only if it does not contain any odd cycle. Have you all seen this lemma before? Yeah, you can quickly prove it if you have not. Like if there is an odd cycle, then see how it would look like in a bipartite. It's not bipartite. And if there is no odd cycle, you can fold the graph and make it bipartite graph. So I'm not going to prove that. Yeah. So now here is a small exercise. Here is a graph. Red is a matching. Okay. Green is not. So can you find the maximum matching? I'm telling you the maximum matching will have size 3. So can you find me a maximum matching, that matching of size 3, which has this green edge? One of the green. Forget this green. Just find me one maximum matching which has this green edge. Is it possible? This maximum matching does not. Is there some other maximum matching which has this green edge, or this green edge for that matter? I mean, this edge cannot exist, because if it does exist, which means this edge is not there, this edge is not there. But okay, here it is. Here it's a simple. You will get an alternating path where both of them are not mixed. But what about this? Yeah, okay. Yeah, so you cannot construct a graph which has a maximum matching. This has any of these green edges. So some edges never participate in any maximum matchings. When whatever maximum matching you can define a set of edges and say I don't have to care about this edge if my goal is to find a maximum matching. Okay. So we want to see what are these edges that never appear in any of the maximum matching. Is there any characterization of such edges, or are there edges which always appear in all the maximum matchings? Like this is what we want to study. Okay. So for that we will look at this very classical result called as the Delmage-Mandelson decomposition. So don't get scared by the term. And just names. So we are given a bipartite graph. So I am going to and a matching M, a maximum matching M. I am going to label these vertices as either even or odd or unreachable. So what is an even vertex? If it is reachable from an unmatched vertex by M alternating paths of even length. We will take a look, understand the definition better. So, is there an unmatched vertex? Believe me, this is a maximum matching. Okay. So, is there a unmatched vertex? This is an unmatched vertex. Is it reachable from an unmatched vertex with even length alternating path? It's trivially true. It's reachable from itself with a zero length path. Right? Zero is even.
Which vertex what are we talking about?
We are looking at unmatched vertex now.
Okay.
These two are unmatched vertex. And the definition of even is simply it's reachable from an unmatched vertex. Here it is reachable from itself by a unmatched vertex, by an M alternating path of even length. A zero path is a M alternating even length. That's okay. So I am going to label, forget this label, I am going to label this as E. This vertex. Is that okay? Even is going to be labeled E. So now, a vertex is odd if it is reachable. Yes?
Can something have two labels?
We will see that in a.
Because the one you mark E at the bottom right, it's reachable to itself. Oh, I'm sorry.
It is even. If it is reachable to itself, now the zero is even.
But can it have both?
That is a very good question. Like, can it have even and odd? Because it's reachable from one with an even alternating path, from some other it's an odd alternating. That's exactly we will see in a. Just give me 2 minutes. So here this vertex is odd. Why? It is reachable from an unmatched vertex with a one length alternating path. Then here is a two length alternating path. The path of our interest must be alternating. That's you must be considering only alternating paths. Then look at those paths and see their length. If it is even, then simply mark it as E. So this is an odd length, odd vertex. Like this is the 1, 2, 3. It is reachable from an unmatched vertex with a odd length, 3 length, alternating path. Therefore, it is marked O, and therefore this is E. This labeling, this is the definition of even and odd. Clear? E, because this is like this is unmatched. 1, 2, 3, 4, 5. I mean, sorry, 1, 2, 3, 4.
So is it possible that a vertex is both even and odd?
Yes, that is the first question that we will see in just next slide. So, but the definition clear, even and odd. So you have to do this for all the vertices. Like take this vertex, it is even because it's reachable from itself, it is unmatched. All the unmatched vertex, they will immediately get E for free because they are reachable from themselves. And once that is defined, see all the vertices that are reachable from either even length alternating path or odd length alternating path. Just mark them. Okay. So here there is no clash happening. Like there is no vertex which is getting from two different unmatched vertices, one even, one odd. Yeah, this is good. So now these vertices were never reached by any of the unmatched vertices, and they're reachable in general sense, but we have limited ourselves to only alternating paths. It's not reachable from using an alternating path from either this or either this. Okay, so we are going to simply name them U, unreachable. This is the labeling of a graph defined with respect to a matching. At this point, it is not clear why this labeling shouldn't have any clashes. Yes.
Why that vertex is unreachable? Explain it.
Yes. So we took this. These are the only two unmatched vertices. From this, whatever is reachable, we marked it as even and odd. These were left, meaning like from here. Can you see? Is there any alternating path? If you take this, So if you from here, if you take this, it is not alternating. It is unmatched, unmatched. I mean unmatched. It should be alternating. Yes, we saw the definition of alternating paths. Like, yes.
So if for a vertex it is becoming both even and odd, then we can take the union of both the paths, it will become an augmenting path.
Yes, we will just see that in a second. Like, I mean, is there any questions about the definition of it?
So the remaining vertices are unreachable.
Yes. If it is reachable by any unmatched vertex, we are going to label it either even or odd. If it is not reachable from any of the, by reachable I mean reachable with an alternating path. It is not reachable from any of the unmatched vertex, we are going to label it as unreachable, U. Is this okay? There is an alternative definition which is much simpler. You can see the equivalence like easily on your own. So there is an iterative way to construct this labeling. Mark all unmatched vertices as E. I have marked all the, I mean, marked 1 here. Then mark all neighbors of E as O. Like if there is an E, mark all the neighbors of E as O. So this gets O, this gets O. So for every O, mark matched neighbors of O as E. Not all the neighbors, simply the match. We want alternating. If the vertex is O, the propagation happens only through the match. So this gets E because this is the matched neighbor of O. This does not, like I mean this does not. And here also it propagates. You just keep repeat until all the vertices are labeled. If something, if you run out, I mean if you have saturated, then mark the unreachable as unreachable. Is this definition easier? Like, yeah. Just take a vertex, I mean first start all vertices as E, unmatched vertices, and then for every E, if there is E, every neighbor of it becomes O. If a vertex is O, all the matched neighbors becomes E. Keep repeating this. Now the first, this is another, yeah. So first claim is that given a maximum matching, every vertex gets a unique label. That is, no vertex is marked both even and odd. First of all, it cannot be named unreachable and even, right? Because if it is even, why is it unreachable? I mean, unreachable is not reachable from any of these vertices using alternating path. So the clash can happen only if it is even as well as odd. I am claiming that it will never happen. Like fix a matching, there is no clash. Every vertex will get either even or odd or U. Do you see this? Is it obvious or should we go to?
If you take the union of both even and odd paths, it will become an augmenting path, which will
Correct.
be a contradiction.
Take a vertex which is marked even. Okay. Why is it even? Because there is an even path, which is alternating, and which is reachable from a unmatched vertex. Let's say V1. It is even. Suppose it is getting odd in another path. How can that path be? Like there is another vertex V2, which is also unmatched, from which this labeling is propagating and it is getting even and odd. But then this is an augmenting path. It starts with an unmatched state, ends with an unmatched state. It's alternating. Here also it's alternating, it continues to alternate. Which means our original matching is not maximum. We have an augmenting path, contradicting to our assumption. So what if V1 is equal to V2 by the way?
Then the paths cannot be even and odd. Oh,
Original
Why?
path would be augmented.
otherwise there could be a
Then becomes
That-
outside.
Then we will have an odd set. Which means the graph is not bipartite. Right. It cannot have, it cannot be V1 and V2 together. I mean, because there is an even path and an odd path. And, I mean, there could be intersections as well, like it can intersect. But
See, we
there
can
will
put the
still,
data on odd
somewhere there will be an odd cycle. A bipartite graph cannot have an odd cycle. So this is necessary. I mean, if you fix a matching, the labeling is clear. Yes. Given a vertex set can be partitioned as even, odd or unreachable. Whatever gets labeling E, I will put it in even. Whatever odd, I will put it in odd and U. This is a partition. This is hopefully the decomposition. but we will see this is with respect to this matching. Right. The very surprising aspect of this theorem is this labeling does not depend on the maximum matching. Whatever matching you choose, a vertex, if it gets even or odd or u in one matching, it's going to get the same label in whatever maximum matching you choose. This says that this property, the vertex label of the vertex, even or odd or u, is an inherent property of the graph. It does not matter which maximum matching you choose. I mean, is this believable at all? When I first saw it, I did not agree with this. This cannot. Whatever is even, I will try to make it odd and construct a maximum matching or something of that sort. Right, but it turns out this is the most beautiful part of this theorem. There is more to this theorem. So we will see that in a couple of cases. So consider two arbitrary maximum matchings m and n. They are both maximum, therefore they will have equal number of edges. One cannot have more edges, it's both maximum. So what will m delta n look like? They will be even paths, even cycles and isolated vertices. There is no odd path because they are both equal size matchings. They will have same number of green and red vertices. With me till now? So now consider so every vertex is here. I am not deleting any vertices, I am only deleting edges. Okay, I am deleting only edges. Every vertex is here. Let's look at vertices that appear on even paths.
Can you repeat why there will be no odd paths?
Because they both are maximum matching. They both are maximum, meaning they both have the same number of edges. The edges that appear in both get deleted. Now here there cannot be more red edges than green edges. If there are, then m is bigger, but we know m and n both are.
There are two odd paths, one where this has more edges, one where that has more edges.
If there is one odd path, okay, here, that's an odd. No. Even if there is just one, if there are two odd paths, consider one odd path, that's augmenting for one of them.
That was what I mean.
Yeah.
There's an argument in between, that's what.
Yeah, okay. So, it cannot be that it's odd. Every component here is even, except the isolation. So, look at the vertices that appear on an even path. Okay. So, what can you say about V1? Is it matched in the red at all? It's not matched. Because we know that it is not matched in the green, because it won't be matching. So, if it were matched in the red, it must appear here. We have all the edges that appear in exactly one of the matchings. We have deleted the ones which is not at all in any of them or in both of them. We know this edge from here is not in green. So if it was in red, it should have appeared here. V1 is not matched. If it is not matched, what is the labeling it gets? Even. So it is even. So it is no. So this gets E. The minute this is E, we know the red labeling of the entire vertices. It's all even or that is set. Now look at V2. Is it matched in N? V2 here. Is it matched in the red, green matching? It is not, for the same reason. So this will get green E. So the minute this is E, this is odd, this is everything propagates, and at least in paths they agree. Is it okay?
Yes.
So now we will see the labeling of M and N are same for all the vertices that appear in even paths. So what vertices are remaining? There are cycles, there are isolated vertices. We will see cycles. Like consider an isolated vertex first. Just an isolated vertex that is unmatched in both. Okay, there is a vertex that is not matched in both. So it will appear as an isolated vertex. They will both be E.
Yes.
That's obvious, right? I mean, they are both unmatched in both, so they are both EE. So the cases that we have is isolated vertices that are matched to the same vertices in both. I mean, a vertex can be isolated for two reasons. Either it is not matched in both of them, or it is matched to the same partner in both of them. Therefore, this edge got deleted in the symmetry prefix. So we have covered unmatched. So this is one that is remaining. And then vertices that appear in even cycles, that we haven't covered. Consider the case of an even cycle. Okay, and suppose I am considering one case. Suppose this V1 is labeled as O in red match. Okay, so how did it get O? It must be reachable from an unmatched vertex in red through an odd length cycle, odd length path. So let's say this is how it looks like. There is V2, and which is unmatched in red, and that is how the labels propagated, and it hit the cycle and it gave O for V1. Okay. Now, question is, if a vertex is unmatched, it's either a vertex, either an isolated vertex or endpoint of an path. Do you agree with that? I mean, a vertex is unmatched. It cannot be part of a cycle because every vertex in the cycle is matched to both. Okay, so it should be either path or a isolated vertex. Not any isolated vertex. It's unmatched isolated vertex. We just saw if it is unmatched isolated, it will get even in both. If it's part of a path, it will get same labeling both. Therefore, if it is unmatched, it is going to get same labeling in the green as well. So the minute this is same, this will propagate till and it will hit the cycle in the same label, and therefore the entire cycle will have the same label. This the minute this is matched, all this is fixed, like it's rigid. Do you guys see the proof here? Like, I mean,
Can you please repeat the starting of this proof?
yes. So why is this O? The meaning of O is it is reachable from an unmatched vertex with an odd length alternating path. Let this be the odd length alternating. This is unmatched. We saw unmatched vertices have the same label in both. Why? An unmatched vertex is either in the endpoint of a path or is an isolated vertex. Unmatched cannot be part of a cycle, another cycle here. Because what is the meaning of a vertex coming in a cycle? It's matched in both, one in green, one. If it is part of a path, we just saw it has same. If it is unmatched in both, it will have both E. So this is the same. Therefore, this will propagate, and therefore the entire cycle will come. The only thing that is, we assume this is odd. Similar thing can be done if it is even as well. Now, we haven't checked the unreachable ones, but let's get ahead of ourselves and just see the vertex that is matched to same vertex in both M and N. Like this is V1 and V2, they both will be isolated in the symmetric difference because this edge gets deleted in the symmetric difference. But again, a very similar argument can be done. If this is E, that must have been, if this is O, it must have been reachable from an augmenting or an alternating path, which is unmatched. Unmatched will get the same labeling in both. That will propagate back and give it the same label for V1. So so it will get both same labeling. So therefore, we proved that for all vertices, if the even and odd they match. Like if it is even in one, it will be even in other. If it is even in other, it will be even in this one, and odd also. So the remaining vertex U should also match. It's a partition. So we know that it's a property of the graph. It is nothing special about which matching you consider. So another thing that we will see is in any maximum matching N, every vertex O is matched to a vertex in E. First of all, E is matched and is matched to a vertex in E. It cannot be matched to something else. So if a vertex in O is unmatched, what can you do? It's an augmenting. Like if a vertex in O, it's O, because there is some other unmatched from it. This is an augmenting. So it must be matched. A vertex in O cannot be matched to a U, because then why is this U? I mean, make it E, right? So can a vertex in O be matched to another O? No, if it is, suppose a vertex in O is matched to another O. Why is this O? Because there is some path which makes it O. Why is this O? There is some other, possibly from the same, in which case we will have odd cycle. If we don't have an odd cycle, this entire thing is an augmenting path. Is that all? So every vertex in O is matched, and it cannot be matched to U, it cannot be matched to another O, it must be matched to E. Okay? I'll take two more. In any maximum matching, and another thing is every vertex in U is also matched, to another person in U. Why? Vertex cannot remain unmatched. U. Why? If it is unmatched, what is the label? What is the labeling that it will give? E. But we are saying it's U. It cannot be unmatched. Vertex cannot be matched to a vertex in O, because then it will not be U anymore. It will be E. If it is matched, the labels propagate from O through the matching edges, and it would have been E. So it must be matched to an E, because the labeling propagated through a match edge from an O. I'll share this. I'm running slightly out of time. I will. Okay. Okay, then yeah, I have very few slides. So it cannot be matched. It cannot remain unmatched. It cannot get matched to an O, and so if you consider any matched vertex is E, because it propagated, it is E because the labeling was propagated through a match edge from O. It's already matched to O. So a U cannot be matched to a E. Right? Take a vertex, if it is E, why is it E? The labeling from an O got propagated through a matched edge. So it's already matched already. It cannot be also matched to another U. So U must be matched to another U. So let's just partition these vertices. There are vertices in O, vertices in E, vertices in U. Every vertex in O is matched to vertices in E. Right? Every U is matched to another thing in U. And I claim this is the entire matching. The matching is going to look, whatever maximum matching you take, it's going to look like this. There cannot be an EE edge. Right? That's a homework that you should try. That there cannot be any other edge. We have proved most of the non-existent sets, but also show that EE edge cannot. So if this is the matching, this is all. Size of the matching is simply how many O's are there and how many U edges by. This is the size of the matching. Yes.
We also have that then the size of O is always strictly less than the size of E. Because you said every O is matched to E, but not necessarily every E is matched to E.
Oh yeah, so this will be more.
Yeah, but how to prove that?
Sorry, could you repeat the
How
question?
to prove that E
Yeah.
has more cardinality than O?
Because every O is matched to some vertex in E. It must be a different vertices, because otherwise it won't be a matching.
Yeah. Right.
So E is at least as big as O.
Yeah.
That's enough to prove. Yeah. So this is how the matching is going to look like. And this is a homework that I will leave. Most of the things that we have, a matching cannot contain an O edge that we already saw. Or an OU edge, because U won't be U. The graph itself cannot have an EE edge. Then it won't be bipartite anymore. That also requires proof, but I'm sure you will, with this much exposure, you should be able to prove that. Or an EU edge, because U won't be U then. So this is the end of this theorem. So to conclude, that Dalmas-Mendelssohn decomposition is partitions a vertex set into odd, even and U, unreachable, independent of the maximum matching. It's the property of the graph itself, and you can, all the nice properties are satisfied. So this is okay. This is used crucially if you want to prove the popular matchings one which you saw in the morning session. If you want to prove it for ties, okay. So the authors crucially use the Dalmas-Mendelssohn decomposition of that graph, the allotment graph, and do something much more, and they give a polynomial time algorithm. I cannot cover it here, but you should definitely check out that paper and see how you know Dalmas-Mendelssohn decomposition, you know how to do it, strict ordering. You should be able to follow that paper and understand how they are using this to work out another algorithm for the case of ties. Yes, so this slides PDF will be available right now. It will also be available in the website. But if you want to work out the details, you can download them immediately. Like, thank you. If you have any questions, please let me know. Thank you.
Yeah, thank you, Vishwa. Here is a token of our appreciation.
Thank you.
people who went to the washroom or something, I think. That's right. Yeah, I think we can.
Yeah. Can you hear me? Am I audible in the back? Okay. So let's start today's lecture. So yesterday we started the series called Introduction to Differential Privacy. So we talked about overview of data privacy, why we need privacy, and how can privacy be breached by launching several attacks. Specifically, we talked about linkage attack and reconstruction attack and membership attack. So today we'll briefly recap some of these nuances of these attacks, and then we'll go to a solution for all those attacks, which is differential privacy. We'll define differential privacy formally. We'll talk about properties of differential privacy, and then at the end of the day, we'll move towards basic mechanisms to achieve differential privacy, and we'll prove privacy guarantees as well as utility guarantees. So if time permits, we might also go to differential private algorithms with applications to ML. All right, so recap that yesterday we discussed the attack landscape. So there are two types of attack we have discussed in detail: reconstruction attack and membership inference attack. So this is a line for error alpha for releasing aggregate statistics. This is the error we can permit when release some aggregate statistics. So if the statistics is of the form of average statistics, like releasing a sample mean, then we have seen that if the error is less than 1 by square root n, then reconstruction attack probably succeeds if number of queries made is order of n, which is linear in n. Okay. Now in this region, when the error alpha is between 1 by square root n to square root k by n, then membership inference attack succeeds if number of queries made is greater than or equal to order of n. That we have discussed yesterday. So now, what was the ultimate takeaway? That using too many statistics with too much accuracy can necessarily determine the entire data set when the error is less than 1 by square root n by using reconstruction attack, and when the error is between this 1 by square root n to square root k by n, then we can actually make membership inference attack to reveal the presence of an individual data in the data set that we have discussed yesterday. So we concluded yesterday's talk by the following need, that we need a quantitative theory that tells us this: how much is too much and how many is too many. That how much accuracy is too much and how many queries are too many. Okay. So this was where we ended yesterday. All right. Let me now recap reconstruction attack for a moment. So we have this data set of several persons. They have identifiers. There are n individuals. Each individuals have some identifiers like name, postal code, age, and sex. And they have some secrets. The secrets simply implies whether the person has some disease or not. So we want to answer queries, k number of queries of the form, which is queries are given by this vector f. Take a dot product with the secrets s, and which can be summed up by using this formula. So these are queries of the form count statistics, and we have seen this reconstruction attack that if we have k queries of the form f1 to fk, and we have some answers a1 to ak, which could be some noisy version of this formula. If the attacker has these k queries and k answers as its input, then it will output us vector of secrets s tilde that minimizes the maximum possible error, right? So fi dot product s tilde is your predicted count statistic, and ai is your reported count statistics. So find a vector of secret s tilde which minimize this error for all query. So this is the reconstruction attack that we have discussed yesterday. And we have also told that, okay, if each query is answered within error, which is much less than square root n, then nearly all of the secret bits will be recovered with a very high probability. If we make a linear number of queries, linear number of queries, and the queries needs to be chosen uniformly at random from all possible 2 to the power n queries. Okay. So we saw that reconstruction attack work when error is much less than square root n. Okay. Now today we will discuss how can we prevent a reconstruction attack even if the error is less than square root n. Okay, so let's start with this. So we have our data set, n individuals, each has identifiers z and secrets s. So we'll try to find a algorithm which will prevent this reconstruction attack. So let's recap that we want to answer queries of this, count queries of this form, f dot product of s, and how, and we will release statistics, and our goal will be to prevent the reconstruction error. The idea that we are going to use, that we'll use the concept of random subsampling to prevent this reconstruction error. So what we will do, from the data set of n individuals, we'll randomly sample m individuals, okay, uniformly at random. So we'll first sample one person, say Alice comes up, and we'll put it in another data set, and we'll sample again, say Alice might come up again. So it's sampling with replacement. So if Alice comes up again, we'll put same data again in the data set. We'll sample again, say Zora comes up, we'll put Zora's data in the data set, sample again, and say Zora again comes up, we'll still put it. So in this way, we'll collect m random subsamples. Note that a number of data points can be repeated here, because this is sampling with replacement. Alright, so this is how we sample for each j in m, 1 to m. First, we pick an I from the n individuals uniformly at random and set the new identifiers z prime j as zi and new secrets s prime j as si. So this mathematical term is basically telling what I just described in words. Right? We just randomly subsample some m data point from the original data set, and the data points could be repeated. So now we have this m random subsamples, right, from this n individual data points. So instead of releasing answers of this form, which is sum over j equal to 1 to n, phi of zj into sj, we will release the following answer. So we have m subsamples. So we release the following answer: a dash is equal to n by m, sum over j equal to 1 to m, phi of zj prime and into sj prime. So what does that mean? That means we have taken these random subsamples and we have released the count statistics for this m random subsample only, not for the entire data set. We have released that and we have multiplied that with n by m. This is the, say if your n is 100 and if we select m equal to 10, we'll multiply this statistics by 10, just to make sure we are comparing on the same scale, because here we have n data points, here we have only m. Just to make sure everything is on the same scale, we'll do this multiplication. Now, so this kind of queries were asked, right? Given by f, which is basically telling that count the release some count statistics, and these answers of a dash are released by the, say, think about this insurance company example. So how many person older than 40 has the disease? So this kind of answers, which are this count statistics. But this now answers will be different because m individuals were randomly subsampled from the data set and their statistics are revealed, not the statistics of the entire data set. Okay, so now we launch the following reconstruction attack with this, because we have now answers of the form a dash. So we have queries, same queries f1 to fk, and the answers of the form a1 dash to a1 dash k. So these answers are coming using this formula. Okay, so our reconstruction attack is same. Output secrets s tilde that minimizes this error for all queries. Right, same reconstruction attack for these answers. Okay. So now let's see whether we are able to prevent this attack or not. Okay. So now note that the hypothesis, right? Note that what will happen, that we can show that with high probability, if we release answers of this form A dash, right? Given a query Fi, we release an answer Ai dash, right? So, and we try to bound this error, which is the true count statistics for the query Fi and the reported released answer using this random subsampling, which is Ai dashed. We try to bound the error between these two and for all queries. And we can prove that this is upper bounded by square root n log k. We can prove that using concentration bounds. So I will not go to the proof, but you can convince yourself that with high probability we can show that. So what does that mean, right? So this is the true query and this is the released answer. So the error will be bounded by square root n log k, right? So the error is square root n log n if number of queries are order of n. So right, so since see now recall the reconstruction attack, right? We know that reconstruction attack for efficient reconstruction attack to succeed, we need a linear number of queries, order of n. So if number of queries is order of n, the error of this release statistic is order of square root n log n, right? So this we can show. So now recall that we know that reconstruction attack requires error much less than square root n, that we have discussed yesterday. The reconstruction attack requires error square root n to succeed. Okay. So here the error is of the order square root n. It is not much less than square root n. It's of the order square root n. Right. So since the error is of the order square root n and reconstruction attack requires error much less than square root n, we can tell that subsampling prevents reconstruction because error is much higher than what reconstruction attack needs to succeed. So subsampling probably prevents the reconstruction. Right? So instead of releasing the entire statistics from the dataset, if we randomly subsample m data point from the dataset and release the statistics for that subsampled set, then we will be able to probably prevent reconstruction attack. This is what we have now just established. Okay. But now thing is, so we have now a strategy which is random subsampling, which is preventing reconstruction error. That means no one can guess that Zora has the disease, right? So Zora's secret cannot be reconstructed. So then you might think that, okay, so this is what we need. We are able to protect Zora's privacy, right? So no one can reconstruct Zora's disease, right? But that's the question we want to pose. Does subsampling give privacy guarantee or not, right? It turns out that the probability with which Zora's data lies in the subsample is m by n, right? So from n data points, we are sampling m points. So the probability and samples are, we are doing sampling with replacement. So the probability with which Zora's data lies in the subsample is m by n. So if n is your 100 and m is say 20, then with probability 1 by 5, Zora's data will lie in the subsample, right? So the same privacy concern will remain, right? So the privacy concern which was there before, when we are releasing statistics from the entire data set, with probability 1 by 5, same privacy concern will remain in the new release statistics also. The probability have been reduced, but the same concern is there. So we cannot concretely say we have been able to protect privacy of Zora because just doing this kind of simple subsampling. So we need something more rigorous. We need a theory to give accurate answers. That means we need a theory to give less errors as well as some rigorous privacy guarantees, and we need to come up with a definition for that. So just randomly subsampling some points from the entire data set will prevent reconstruction error, but will not rigorously prove privacy or rigorously gives privacy guarantee.
In this case, if we ask the same query multiple times, we can ask the same query a lot of times and then maybe take the average of it. That will help us in like determining the actual value instead of just
Yes.
approximate our
Yeah. If you do same query multiple times, you can probably do some reconstruction, but doing the same query multiple times. But depends on case by case basis. But this is kind of worst case guarantee that you can use. Okay. So now we have established that we need a notion of a definition of privacy, which the simple random subsampling won't give us. So we'll put the following requirements. So you want to protect against arbitrary auxiliary knowledge.
Aren't we doing the k times in the last? Aren't we already considering the k queries?
Is k queries, yes.
So like if you are discussing.
Oh, he asked k same queries. K same queries multiple times, right? And now if we samples we have to do m random samples for the same query multiple times, right? So similar samples might come more often. So that was his question. If we do the same query multiple times, then what will happen? So on a case by case basis, there might be a case some good amount of information will be reconstructed. But in general, if queries are completely different, then this is the result that you will get. Okay, so we need to define some requirements of privacy. So remember we have discussed this linkage attacks yesterday, right? So where people have some arbitrary information, right? So Netflix data was hacked, Netflix data, privacy of Netflix data was breached using publicly publicly available IMDb data, right? So we need to protect against those kind of things. We need to protect against this arbitrarily auxiliary knowledge that people have, right? We have to be robust to whatever public knowledge the attacker has that we cannot predict she knows or she might know in the future, right? Like any kind of public information the attacker might have, we need to protect from that. Okay, now think about this multiple query question, right? So if we ask multiple query from a same statistical data set, right? Think about this 2k anonymous tables that we have shown one example. But if you have 2k anonymous tables, you can just do some mapping between these two tables and get people's data, right? So multiple analyses are getting performed on same people data, right? So we need to protect against those also, right? We need to be able to track how much information is leaked when asking several questions about the same data. So we need to protect against those also. And third is while doing all this, we also need to do some kind of meaningful statistical analysis from the data set. Just to maintain privacy, we should not forget about utility. So this is the requirement, 3 requirements of privacy that we want. Protect against any arbitrary auxiliary knowledge so that the reconstructions, the membership inference are not possible. Protection against multiple analysis, as well as think about getting some meaningful statistical analysis of the data sets. So these 3 requirements we need. All right, so let us try to define privacy. Okay, I think there is some slide issue, right? So our first definition of privacy is an analysis of a dataset is private if the attacker's belief about an individual stays the same after they see the result as it were before. Okay, so attacker has some knowledge, some prior knowledge, some auxiliary knowledge before time, right? So no matter what they know before time, their belief about an individual stays same even after the statistical data analysis has been performed on the entire data set on which the individual's data belongs. Okay, so the knowledge doesn't change over time. All right. The thing is, if we put this as our privacy definition, that we want an analysis of data set which will not release anything extra which was known before, then you can see that it is impossible to reveal anything, right? If the result is to depend on data, right? If your statistical analysis needs to be useful, right? Then if you put this condition, then you cannot release anything meaningful. If we impose this condition, the statistical analysis will be useless. because we are not getting anything, releasing anything meaningful, and will not get any utility. So this definition won't work. Yeah, so and before and after requirement can be sometimes unachievable after unachievable if the adversary has some auxiliary knowledge. So now for this, think about this example. For a person Alice, she is a smoker, okay, and her health insurance company knows that she is a smoker, okay. So now a data analysis, this is the prior knowledge the health insurance company has, right. Now a data analysis is being performed where a lot of individuals are called who are smokers, and the data analysis takes a lot of individuals' data and try to analyze whether smoking and passive smoking causes cancer or not. This data analysis has been performed, right? And the result of the data analysis comes that okay, smoking causes cancer. Obviously, the health insurance company get to know that result of the data analysis. It's in public. It knows okay, smoking causes cancer, and it has a prior knowledge that Alice is a smoker. And after the data analysis, the result of the data analysis is smoking causes cancer. So it can guess okay, so Alice might have cancer, right? So then what the company do? Company raises Alice's insurance premium, health insurance premium. It raises because Alice is prone to cancer. So I will raise Alice's health insurance premium, right? Now can you tell me whether does this thing breach Alice's privacy or not? No, right? So why?
Well, the information is so trivial, it does not give you any more information about the person.
Yes. So whether Alice was present in the study or not, the output of the analysis would have still come the same, right? It will still say the smoking will cause cancer. Whether Alice was part of the study or not, it doesn't matter. The company would have raised the premium regardless of Alice's participation. So if you follow this definition, right, it quite doesn't work well. So we are not quite there. And actually, this kind of correlations is the kind of things we want to able to learn from doing statistical data analysis. Statistical data analysis should give us this kind of answers. Then only it remains meaningful. So if we follow this definition, then we are not quite there. Okay. So now let us try to modify this definition. All right. Our second attempt is, so an analysis of a dataset is private if the attacker would draw same conclusion about an individual, whether or not her data used in the analysis, right? No matter what they know before the time. So whether some individual's data was used in the analysis or not, the attacker's conclusion about that individual will not change. This is our second attempt at the definition. All right. So what this definition gives, right? So we cannot infer membership of an individual in the data set, right? Because the definition actually gives us that, right? So whether the individual was there in the data and not doesn't change the conclusion about the individual, right? So we cannot infer the membership of an individual as well as we cannot reconstruct any sensitive information about her. So if we put this definition, then we can protect against membership inference as well as reconstruction attacks. We need to put this definition and we need to analyze, we need to do analysis of a data set that satisfies this definition. Then we can protect against membership as well as a reconstruction attack. Okay, now think that, okay, so now all this thing has to hold irrespective of whatever auxiliary knowledge the attacker has before the analysis was performed, whatever auxiliary knowledge the attacker has, this won't change this definition, right? So it will only, so this analysis of the dataset will only be successful if the analysis is some random. It's not a deterministic analysis. Otherwise, it will not be possible. we need to do some randomization in the analysis so that the attacker's conclusion will not change whether the individual's data was used or not in the analysis, right? So let us see why randomization is necessary, right? Let me give an example why randomization of the analysis is necessary. Okay, say this simple scenario, say A is an algorithm which is a non-trivial and deterministic algorithm. That means A doesn't use any kind of randomization. If you ask a question, A will report the true answer. Okay, and non-trivial means if we ask two different questions, A will give two different answers, not the same answer. Now think about two data set. I think let me put the pictures. Yeah, think about two data set D and D dash, right? If you can see, D and D dash only differ in a single record. Only one person's data is being changed. So D has 5 persons data, 6 persons data, and D dash has 5 persons data. So D has only one extra data. So only one record D and D dash differs. Okay. Yeah. Now the attacker asks same query to both the data sets, right? So think about an analysis being performed on both the data sets. The attacker asks same query to the analysis. Okay. Now the analysis which is getting performed on the data set. So if the attacker asks the query Q to the data set D, the analysis reveals the output S, and the attacker asks query Q to data set D dash, the analysis reveals output S dash. Okay. So see, since the A is a non-trivial deterministic algorithm, the outputs S and S dash will also be different. So S has 3 entries and S dash has 2 entries, and one entry is different. Okay, or not one entry, can multiple entries can be different. So the point is outputs are different. So now even if the adversary knows, okay, the input data set of the algorithm is either D or D dash, right? Then it can learn which record was missing. Just seeing at the output, and the algorithm is non-trivial or deterministic algorithm, it will know whether D was used in the analysis or D dash was used in the analysis. And so he can know, or he can infer the information about this, the record which was not present in D dash but present in D, right? So without randomization, we are not being able to robust to auxiliary knowledge. The auxiliary knowledge here is that adversary knows that either one of these two data sets has been used in the analysis. This is the auxiliary knowledge. So we are not be able to protect against this kind of auxiliary knowledge if the algorithm is just a deterministic algorithm. So we need to make some randomization so that the adversary cannot use his auxiliary knowledges. Okay. So we are now converged on this definition that, okay, if we have an analysis of a data set which is randomized, then the attacker would draw same conclusions about an individual, whether or not the individual's data was used in the analysis, and no matter whatever the knowledge that attacker has before time. So this is the definition that we see that we cannot infer membership as well as we cannot reconstruct. Similarly, linkage attacks cannot also be performed, because if we use randomization, then we are robust against auxiliary knowledge. So this will be our definition, and let us formulate this definition with differential privacy. The differential privacy is exactly the definition that I told you in words. It has been coined by this seminal paper by Dwork, McSherry, Nissim and Smith in 2006, and a flurry of work followed, and based on their work they have been awarded in 2017 Gödel Prize for pioneering differential privacy as a measure of protecting individual data privacy. Alright, so let us now give the formal definition of differential privacy. So we have a randomized algorithm now, okay? So algorithm needs to be randomized. So there are some random coins which determines algorithm's randomness. There are n individuals which constitutes the data set. let us denote the data points at x1 to xn. There are n individuals. And the algorithm outputs A of D. D is the data set. And so since this is a randomized algorithm, the output will be a probability distribution, right? It's not a deterministic algorithm. It will be a probability distribution. So the distribution of the output looks like this. Now let us consider a thought experiment. So we need to protect if only one record in the dataset is changed, that attacker would not be able to tell whether that person's data was there or not. So we consider this thought experiment. So we take the dataset, we change the dataset in a following way. We either change one person's data completely, we add a new data, or we remove one data. So this is how we can change the dataset, right? Only in one entry. If we change or replace one data, it differs by one entry. Similarly, add or remove only differs by one entry, two datasets. So now we'll try to ask, will the probabilities of the outcomes change or not? If we do this change and train and pass the changed dataset to the same algorithm, will the probabilities of the outcome change or not? Let's do that. So what we are doing here, we removed 1% data. So now we have n-1 data points. And we pass that new dataset to this randomized algorithm. We're calling new dataset as D dash, and A of D dash is the output of the randomized algorithm on the new dataset. And since it's a randomized algorithm, it will be a distribution. So probability distribution of the output is A of D dash. So this is the original dataset. Now we do a thought experiment where we just remove 1% data and running the same algorithm, and we are getting A of D dash. Okay, and obviously the two distributions are. So we need to see whether these two distributions will change or not, right? Now think about if two distributions change too much, and if the attacker has an auxiliary knowledge, then either D or D dash are used in the training of the algorithm, it will be able to know the differing record if the distributions change too much, right? So what we want, what differential privacy requires, that both the distributions, the blue curve and the red curve should be close to each other. That means if we plot both the distributions together, this error, this ratio, right? And in the y-axis is the probability, and x-axis is the output range of the algorithm. For any output of the algorithm, the probability of AD and probability of AD is this point, and probability of AD dash for a particular value of the output should be small, right? The ratio of these two should be small. Then we can only tell that both the distributions should be close, and it should hold for any output of A. For all output of A, the two distributions should be close in the sense that the probability of AD and probability of AD dash, you take the ratio, this ratio should be bounded by a small number. That's what we want. And that is the requirement of DP. Both distributions needs to be close.
The probability we mean the density.
Probability density for this kind of density curve.
Yeah.
For discrete random variables, it will be probability mass function.
Can we run KL divergence to measure the distance between those?
Yeah, there are notions of KL divergence. You can also do that. Those are advanced notion of privacy. Instead, not KL divergence, something called Rainy divergence are being used. You can think about the generalization of KL divergence. So those are advanced notion of DP. Yeah, but then the notion is if you take two distributions, some form of distributional divergence is bounded. Okay, but for our purpose, we'll just stick to the simple definition that the probability ratio needs to be bounded. All right, let me now define DP formally. So now first doing that, so what we are doing, we are changing, adding or removing one person's data, right? That means two data sets, D and D dash, only differ in 1% data. We are calling this kind of data sets, which are differing in 1%'s data, is neighboring data set, right? Only one change. So now, if the randomized algorithm A is called epsilon differentially private, if for all possible neighboring data set D and D dash, consider all possible neighboring datasets that are possible. Right? Suppose you take n individuals, you can remove first one, or you can remove second one, or you can remove nth one, right? Or you can do change, or you can do replace. Consider all possible this kind of neighboring datasets which differ only in one entry, and all possible output of the algorithm, right? So the algorithm's output is a distribution. So there could be a lot of possibilities of the output, right? So all possible outputs, we have to ensure A, that the probability of the output AD, right, belongs to some set S is upper bounded by e to the power epsilon times probability when the algorithm is run on the change data set D dash belongs to S, right? So this is the probability that the algorithm is run on the data set D and the output belongs to some set S, set of outcomes S, and this is the probability that when the algorithm is run on the change data set D dash and the output belongs to some set S. And if you take the ratio of both, the ratio needs to be bounded by this quantity e to the power epsilon. This is the formal requirement of differential privacy. The ratio needs to be bounded. And if we do this, if we do this for all S, then both distribution should be close. We are doing it for all possible outputs. So the ratio is bounded for all possible outputs. So the distributions are close. So similar for the other way around. It's not a one-way relation for the other way around. So the ratio that probability of AD dash belongs to S and probability of AD belongs to S is also bounded by e to the power epsilon. So other way around also. Okay, so from now on we'll stick to this the first requirement where because both are symmetric, we'll stick to this requirement when we'll do the analysis for two neighboring datasets D and D dash, and we'll find the probability that AD belongs to S and probability that AD dash belongs to S, and we need to ensure the ratio between these two is bounded by e to the power epsilon. If we can satisfy this, then we will call that the algorithm is epsilon differentially private. So epsilon is a real number which takes value is a positive real number which can be 0. Then both its inequality is basically equality, or it can take any value in the real number. It can be as high as infinity. If epsilon is infinity, then will the distribution be close or very far away? Very far away, right? And if epsilon is 0, then the distributions are exactly similar. So the value of epsilon determines how much privacy you have, right? If epsilon is very small, we have good amount of privacy. The distribution, the ratio is bounded by very small number. If epsilon is high, the ratio is bounded by very high number. The privacy degrades. So the epsilon needs to be close to 0 or very small to guarantee a good amount of privacy. Okay, this is what epsilon differential privacy is. Okay, this is our definition of differential privacy. Okay, so now as we have mentioned, any privacy preserving algorithm will have two conflicting objectives. How much privacy you want to ensure by setting different epsilons. Epsilon small means high privacy, epsilon large means low privacy. It also needs to balance between the utility, right? It also needs to balance between utility and privacy both together. So why utility is required, as we have discussed yesterday, that utility needs makes us enable to do some meaningful statistical analysis of the dataset, right? Think about inferring about a population, releasing a census report. So you need to release statistics which doesn't report junk. Think about training machine learning models. It should be accurate enough. Similarly, privacy requirement is protect individual level data against all possible attack strategies like linkage attack, reconstruction attack, and membership inference attack, and any auxiliary information that the attacker may have, right? So these two requirements, and we need to balance between these two completely. Continuously we need to balance between these two. Any question now?
What does epsilon physically signify? Is it the ratio bound or some?
Yes, epsilon basically tells what is the ratio bound. E to the power epsilon is the ratio bound. If epsilon is high, then the ratio bound is high, right? So the distribution could be very far away from each other. So that means privacy is lost. And if small, then otherwise. No, we have not formulated. We have not formulated utility. We'll do it on case by case basis. When we talk about different private mechanisms, we'll do case by case basis.
So when we are trying to prove these inequalities for particular epsilon, suppose this output of the algorithm could be any real number, so, but any subset of to prove it for any subset of real numbers is a very difficult job.
No. So this is a distribution over real line, right?
Yeah, and subset of real numbers is quite rich. I mean, it's not even.
It's quite rich, but if you are aware of measure theory, that means if you have a
all possible subsets.
Yeah, all possible subsets which is measurable on a these are distributions, right?
Yeah.
Which has to be measurable, not for all possible subsets.
Exactly.
It is all possible measurable subsets. So those who didn't understand this, so we told that okay, so this needs to be satisfied for all S, right? There might be some S, right? What is S? This is a set of outputs in the distribution, right? So there might be some set of outputs. For that, the probability of AD or AD dash is 0. Right? There might be some set of outputs, right? So for those kind of subsets, it won't work. It will only work the subsets which has non-zero probabilities. So that means all possible measurable subsets. Think about like that, okay?
And define probabilities. Define.
Exactly.
If it's not measurable, then we cannot even define them.
Exactly. So for now, let's ignore this. Think about everything is measurable. All good things are there, and we can compute this for all possible. Compute the probabilities for all possible sets. Then we need to bound this. Any question? Okay. So far, we need to balance between privacy and utility, right? Okay. So let me now discuss what DP promises and what DP doesn't promise, right? So the requirement of DP is two distribution AD and AD dash should be close to each other and can be only off by a factor e to the power epsilon. Right? The ratio of between these two distribution needs to be bounded by e to the power epsilon. So what DP promises is, okay, so whatever an attack, that's the definition, whatever an attack learns about me, it could have learned from everyone else's data. Right? Think about this. Alice is a smoker example. Right? It gives protection from the attacker's auxiliary knowledge. Any auxiliary knowledge that whether D was used in the training or D dash was used in the training, this kind of auxiliary knowledge if the attacker has, DP also protects because we need to satisfy this definition for all D and D dash. Right? Then if we can satisfy this kind of protection is also guaranteed. It also gives you graceful composition for multiple queries, right? So this kind of this kind of 2K anonymous table attack, where you link between two tables. So this kind of things also DP protects. That we'll see. We have not discussed how DP does that. We'll see along the lecture. What DP doesn't promise? It is not that it promises everything. It doesn't promise for protection for information that is not localized to a few records. Right? If this n data points are the same data points, one person's data has been used in all the n data points, and you can see the DP doesn't able to protect that. Because even if you change D dash, the distribution will almost be same. So DP won't be able to protect. So now giving privacy where none previously exists. If there is no privacy, DP cannot protect that, right? Think about this Alice example. So whatever the result of the smoking study was, it will still inflate Alice's insurance premium. So Alice's privacy didn't exist, so DP cannot provide that also. And also there is no guarantee that if I protect a data set, the individuals won't be harmed, right? There is no guarantee like that. So this is the promises. It's the algorithmic way of achieving privacy of individuals in the data
Can
sets.
you elaborate on won't be harmed, meaning won't be harmed on what basis?
Won't be harmed means like if your information is revealed in the public by auxiliary knowledge, you won't be harmed. Right? DP won't be able to get that.
No, because if my information is revealed,
There is some harm means against auxiliary knowledge. It
but what if I misunderstood, but even if I have auxiliary knowledge, so DP is giving protection from the attacker's auxiliary knowledge, so I shouldn't be harmed, or no?
no. So think about this smoking example, right? So, right, smoking example. Alice has been harmed because the premium has been increased, right? So here DP cannot come and tell that okay, I will release the smoking causes cancer study in a different way, right? Instead of in a private way, so that Alice's premium won't increase. DP won't be able to do that.
Yeah, but it can guarantee that individuals won't be harmed if that is the only data available.
If individual won't be harmed, that is the only data. Yeah, you can tell that. Yeah.
That is the only privacy-induced data there. I mean, if
Privacy-induced data.
if there's data where there's no privacy, it cannot add privacy. So that is
Exactly.
So that is the reason why it cannot.
Exactly. Yeah.
Guarantee.
So if there is no privacy, you cannot add it, and so
And this is the consequence.
yeah. Just think about this example, right? So you have this Alice is a smoker, and the study has been done, right? It is not a differentially private study; it's a normal study. But think about you are doing it a differential private way, that study, right? But still, Alice's premium would have been increased, right? So then that when if privacy is not there, you cannot give privacy. But and also the consequence is that. So when is the lunch time? 12:45. Okay, so before lunch, I think I have 2 more slides. Okay, so there have been a lot of research and deployments of DP. Let me now try to promote DP to you guys. Why you should study DP? Why should you do research on DP? If you are interested in algorithms, why should you try to make differentially private algorithms? If you want to do research in cryptography security, why should you also thinking about differential privacy along with your multi-party protocols and all? Why you also need to do differential privacy? If you are interested in machine learning, statistics, training a support vector machines, or building a chatbot, why you need to think about protecting privacy of individuals, and you should think about training your machine learning algorithms, which is differentially private. If you are interested in game theory, mechanism design, economics, you should design mechanisms which satisfy differential privacy. All these are needed, and there are a lot of research that has been going on for a decade. So there has been research which has done built approximation algorithms using differential privacy. Singular value decomposition, principal component analysis has been studied with differential privacy. Streaming analysis, where you are releasing a stream of data is coming up, and you're releasing data outputs continuously. Differential privacy algorithms based on has been studied, and there are a lot of research going on in this area. Similarly, in security, people have considered multi-party computation along with differential privacy. You have to build a protocol which satisfies multi-party computation, but you also. So what does multi-party computation do? It protects the information against another parties. Suppose I am a honest party and there are dishonest party, and all the parties together are trying to communicate some information. So my information will be protected against against the other parties, who are in the protocol. But my information won't be protected against any arbitrary adversary who has some auxiliary information. So you should try to combine multi-party computation with differential privacy, because differential privacy will give you protection against an adversary. Now think about, so there is another line of research going on, where if we implement an algorithm in a computer, right? So computer cannot process real life values, right? Computer needs to use some kind of floating point arithmetic to implement those kind of things, right? So there has been research which has shown that, so if when we implement an algorithm, say an ML algorithm in a computer, so during this floating point arithmetic structure, some privacy will be breached. So how can we protect the privacy of those algorithms that we are implementing in a real life computers, right? So also there are a lot of computational primitives, like building some kind of secure protocols. Building some kind of secure randomized shufflers has been done using differential privacy. So in crypto and security, there is a lot of scope of differential privacy as well as algorithm. Similarly, statistics and machine learning, think about you're releasing some histograms that are like count statistics. So a lot of work has been done on histograms, different kind of tables, and also our favorite machine learning problem, regression analysis, as well as your estimation and clustering problems like k-means. So all has been studied using differential privacy. Game theory and economics, social network analysis like Facebook data has been studied using differential privacy, mechanism design with differential privacy, as well as building multi-agent systems. So differential privacy is a burgeoning field of research. There's a lot of research going on, and there are a lot of scope. It has flavors of both algorithms as well as cryptography and application. It can be applied to, it is applied to statistics, machine learning, literature, as well as game theory and economics. So the tools you will use from algorithms and crypto, and will apply this to machine learning, statistics, game theory, economics. It's a very not old research direction. It's a new research direction, as well as it's a very burgeoning research direction. And there are companies which are also using DP in their deployments. Apple released iOS 10 and Safari for the first time in 2016 using differential privacy. So your information in Safari will be protected using some differentially private mechanisms. So US Census Bureau releases US Census, where the people's statistics are being released using differential privacy for the first time in 2020. Google has their wrapper framework for analyzing or releasing Chrome statistics, like the usage of different persons in Chrome, in the Chrome browser in 2014. And there are lots and lots of other companies like Microsoft, Uber, they are using DP in some of their products. So not only it's a field of research, it's a very well used tool in the industry as well. Now also there are growing interest from different other communities in using DP, whether we can brought DP into our daily life practice, like communities like law, right? The lawmakers are trying to use DP. In social science, in medical informatics, we're releasing persons' medical informations. In programming languages and also database systems, right? So DP has been used in by all these different communities. Okay, so I think I have promoted DP enough to influence you guys to study DP further, study differential privacy further, as well as think about doing research on differential privacy.
How is it being used in programming languages?
I don't know, but it is being used. I don't know programming languages, but it is being used. There are papers. I can send some, probably put some reference to the papers in the slides, right? I think that will be good, because I really don't know how programming languages, law, social science is being used, but it's being used. So yeah, before we break, I think I'll just give one comparison with other privacy models. So this is a slide you can take. Don't ask very difficult question to me about secure function evaluation, homomorphic encryption. I don't know. So this is the basic summary slide. These all three are different privacy models. One is differential privacy, another is secure function evaluation, another is homomorphic encryption. So these are three privacy models. So in cryptography course, you will probably learn this, right? Secure function evaluation and homomorphic encryption. So what differential privacy does? It protects privacy of individual information. Whereas secure function evaluation protect everything other than the result of a query. So you asked a query, it will protect everything other than the query's result. Right? It will not protect the query's result. DP will protect that also. So individual information will be protected. Homomorphic encryption protects everything. Okay. So what is utility? DP's goal will be to do statistical analysis of dataset, learn a machine learning model, release some count statistics, and secure function evaluation's utility will be to answer any given query, any possible query. Same for homomorphic and encryption, answer any possible query. And now, who is the data holder? That is a very important thing. Whom do we trust with our data, right? So we are using our mobile device every day, right? We are using a lot of apps, and our data is getting transmitted every time, right? And data is getting stored somewhere, right? So DP assumes that there is a server in a company. There is a server which is trusted. That server cannot be attacked. So we can trust the maintainer of that server. So we can store our data in that server. Whereas secure function evaluation tells that we cannot trust the server. Server, who is the maintainer of the server, can also be an adversary or an attacker. So we cannot trust the server. So your private data is stored with you only, right? The users, so us, our private data is stored with us only. Whenever we send our private data, we have to, do some kind of secure function, like kind of security, and send our data. And homomorphic encryption doesn't trust the server also. Okay, it is also same as like users will be the data holder. So DP trusts the server. It protects the individual information, and it tries to do some meaningful analysis of statistical data.
The last two?
I don't know.
Just two different things.
Two different kind of protecting privacy. Yeah.
Perhaps no difference in outcome.
Yeah. Maybe. I really don't know the details of this. I have no idea. So the difference I can tell, the DP versus others.
Okay.
The DP versus others is,
DP trusts the server.
This trusts the server and your individual information is protected. That is the difference, and you need to do some good statistical analysis. So key principle is the DP is a property of the analysis, not of a particular output. You need to make the analysis in such a way, then the outputs are differentially private. DP is a property of the analysis, not a particular output. Whereas these two are the properties of outputs. Alright, I think we'll stop here. Any questions? Yeah. Ratio bounded means that the likelihood of whenever you are training the algorithm, likelihood of an output occurring under the true dataset D versus this hypothetical dataset D dash where you have replaced one item, the likelihood of the same output happening is same. That means if you see these two outputs separately, right? Training and no, you are training an algorithm, a differentially private algorithm, or releasing some counts. Think about computing the average, the sample mean, right? Thinking about that is an algorithm. Your algorithm takes the data, computes sample mean. So whatever the sample mean, these two cases, the whatever the sample mean for these two cases. One case is D, dataset is D, another is D dash, where D and D dash is differed by only one individual's data. The likelihood of both the outputs are more or less same. That means both the outputs should be similarly looking. You just by looking at the output, you cannot guess whether D was used in the algorithm or D dash was used in algorithm. So you cannot guess whether the missing person's data was there in the dataset, trained dataset or not, or the dataset or not. So this is the main